Well, if you work in a business manufacturing things, and especially if you're on the quality or operations team, you might not find it too unusual that your routine quality checks find out of specification parts. And if you're making assemblies, these downstream parts don't fit together well, resulting in excessive scrap, low yield, and if the parts unfortunately got out to the customer complaints. Final analysis, this means losses to the company in terms of reputation and cost. Well, I welcome you to our Statistical Process Control Clinic, Part 1. This is Part 1 of 2 parts. And I hope you enjoy the training that I'm providing for you. Well, I was first introduced to statistical process control early in the 80s. And back in the day, NBC would produce these, what we called white papers, I guess what they called white papers, which examined, in this case, the differences between the US and Japanese management systems. And I refer you to the Google link right there. If you go and swipe that and put that in your Google, you'll find that NBC has provided this document, this show on YouTube. And I would urge you to scroll ahead to part 4, and you'll find an interesting interview by Dr. Deming. The entirety of the white paper made a lot of people very uncomfortable in U.S. manufacturing because it showed the gains in productivity and quality in Japanese products as opposed to U.S. products. So I worked as a supplier in the automotive business, and it raised an awful lot of attention. But as you'll see in part 4, it introduced Dr. W. Edwards Deming and his 14 points and the use of something called statistical process control to improve quality and productivity. He emphasized both significantly, and it created great interest in the automotive and other industries, especially in the automotive industry where I worked. Well, Ford at that time was very, very interested in quality and productivity improvement, and their supplier quality assurance team engaged their key suppliers, which I work for one, to use statistical process control, so much so that they held a number of classes on their sites with their teachers free to use for its suppliers. In addition to that, to reinforce the use of statistical process control, Ford set up quality standards which suppliers had to meet, and their purchasing team stressed the use of statistical process control to improve quality and productivity with their sourcing decisions. Again, I would ask you to take a look at this and now or later, but you'll find it very, very interesting back into the 80s. So I'm Mike Vella. I am recently retired after 42 years in operations and quality. First 30 years with an automotive OEM supplier of safety critical parts, and then the last 12 years of my career in a food manufacturing business. Undergraduate in aviation engineering technology at Western Michigan University in Kalamazoo, Michigan, MBA in finance at Wayne State, and senior member and fellow of the ASQ that's the American Society for Quality. I'm a certified quality and reliability engineer. So you'll see that describing and controlling variation, statistical process control, is just one of the tools that we'll be offering in our practical problem solving toolkit on YouTube. In our introduction here, we want to talk about statistical quality tools. They will allow you to describe the variation in your process. If you think back to the previous little movie of so many, so fast, we don't have the possibility of measuring and checking every item. So how do you ensure, or how do you evaluate quality? That's the challenge. So use of statistical process control, statistical quality control tools will show us how to describe that variation, show us how to minimize the variation, and give us the best quality, and best quality being defined as minimized variation that is right at target. Again, our best quality parts are those that are made the same and made to target. That's the definition of quality. So it's our agenda that we'll be going through, and you'll find that this training is about an hour in Module 1 and about an hour in Module 2. Let's talk about other definitions of quality. First, might be thinking of fitness for use as a definition of quality. Well, what's fit for use? When I take my car to the gas station and fill it up with unleaded regular, I really can't tell the difference whether I'm at brand X or brand Y or brand Z. It's all fit for use as long as the car starts and runs adequately. I guess it's okay. How about water? I mean, we all drink water every day. I drink it out of the tap, I drink it out of the water. They're both fit for use. So when you think about the definition of quality, fitness for use is kind of a basic definition. Another one is conformance to specifications. Well, we all have blueprint requirements or specifications written down in one way or another. For example, if you're buying a car and you're speaking to the salesperson, they're going to tell you that the car has an expected miles per gallon rating. Maybe they tell you, maybe it's on the sticker on the side of the car, that you're going to get 18 to 20 miles a gallon. If you only get 15 miles a gallon, you certainly are not meeting that conformance to specifications requirement. Dr. Deming has a different take on quality. It's a little bit broader. He said the quality of any product is an interaction between the product, the user of the product, their expectations of performance and of service that they can receive in case the product fails or requires maintenance. You can have the best product in the world and use it for a couple of days, weeks, years. If it fails or requires maintenance and you have no way of having it repaired or having replacement parts to fix it, maybe the quality is not so good. So he speaks about quality in a little bit broader terms, especially pointed to a consumer. Let's talk about quality and grade of quality versus range of quality and what we in manufacturing usually deal with. Talk about diamonds. So in terms of diamonds, there's all kinds of grades. Well, you can see that there's different kinds of grades of cuts: round, oval, cushion, princess, pear. I didn't know that there were so many different grades. Each one has a range of quality within it. And the range of quality typically for diamonds is classified as shape, cut, color, clarity, and carat weight. Within each one of those, there's another range. For example, cut. You're going to spend an awful lot more money on a cut that is ideal or super ideal versus one that's poor or fair. So in terms of quality and in manufacturing, your business leadership, your management, your customers, your engineers will determine the grade of quality that you're using. Operations and quality influence the range of quality. So for whatever we're working with, we have to make sure that our manufacturing processes give us the right target and we minimize the variation. That's what we're looking for. We're interested in manufacturing in the range of quality, not so much the grade of quality. Another definition comes from the Japanese, and it's called the Taguchi loss function. I'll get to in the next slide. But what you're looking at there in front of you is something called a discrete loss function. In the middle of the page, you'll see between the lower specification limit and the upper specification, and on the y-axis there's losses, high loss or low loss. As long as we conventionally think, as long as the parts or the product fit between the upper and lower specification, there's no loss. We get to ship it. But as soon as it gets beyond that border that was created by the engineers who drew the specifications or the requirements, there's a lot of loss. Maybe rework loss, maybe scrap loss, but there's going to be a loss. So the question is the quality between those two boundaries exactly the same? For example, if you go out to want to buy a television, and you know that televisions are manufactured on a line, and every one of the little components that go into building a television has some variation, and so as a result, the quality of perhaps the picture color, the temperature of the picture, all the different components that make a quality set are a combination of all these little factors. And you want the optimum quality, one that's maybe right at target, wherever that target is. Well, do you believe that the one that the stock guy goes and gives it to you and you load in your car is exactly at target? How would you know? How do you know that it's not at the low end of the specification, maybe right near the edge? And are you willing to pay your money for something that is close to the edge of the specification, as much money as you would pay for the one on target? And that's the point. Point is that this discrete loss function doesn't really speak about quality, it really speaks about cost. Well, Taguchi's changed the paradigm, especially for the Japanese, when they were clearly making parts back then and now, when their parts all fit within specification. But the argument began just like in the discrete loss function, is what's the rush of reducing variation being a target? Well, they said we define quality as those parts that are close to the target, and therefore they had to quantify to their management that there were losses within the upper and lower specification limits, and that is losses away from target with greater variation. Products that are made like that are not as good and therefore have a loss to society, to consumers, and they wanted to avoid those losses. They quantify those losses even though they maybe were difficult to see on a balance sheet or a P&L, but they quantified those losses and said the best quality, those with reduced cost to society, were right at target. So again, we're defining quality as minimized variation around targeted process streams, and that's the whole point of using statistical process control to improve quality and control processes. So again, SPC and statistical process control, statistical having to do with numbers, drawing conclusions from the analysis of numbers, process, any set of conditions or set of causes which work together to produce a given result, the characteristics of a system we're studying, process, control to keep things within boundaries, to make something behave that we want it to, the way we want it to behave, as opposed to maybe the way the process wants to run naturally. The payoff is statistical tools allow us to describe variation and minimize that variation on target. Okay, minimize variation on target, give us the best quality, lowest cost. The mantra is make things the same, make them the target, provides you and your customers best quality, lowest cost, more reliable, and allows your business to grow. So the different types of way to measure things, there are variables measures and attribute measures. This is what we're going to talk about in terms of variables measures. This is product or process information collected using gauges that provide some kind of discrete data. Variables measure is typically more sensitive to detecting the causes of common versus special cause variation. We'll get to common versus special cause a bit later. It's not unusual that you have less data collection using variables measures. However, gauges are more complex and perhaps more expensive, and the training for operators and people to use those gauges take more time. Examples of variables measurement might be length, diameter, concentricity, pH, and so forth. Variables measure as differentiated from attribute measures. Attribute measures product or process information collected, which compares the portion defective versus total, or the portion acceptable versus the total. Attribute measures are less sensitive than variables measure. The gauges are typically much simpler, maybe simply just your eye. For example, they might be an attribute measure might be pass versus fail, undersize versus oversize with some kind of snap gauge, painted versus unpainted, leaks versus no leaks, and so forth. We're going to review both variables and attributes and how to control the variation in this seminar. So again, statistical process control is a scientific method of analyzing data and using that analysis to solve practical problems, improving quality and reducing cost. SPC is used to improve the quality of anything that is possible to express in the form of numbers. I'm sure it's not unusual that you have supplier quality problems, and they may have supplier quality problems, and as a result, you may have process quality problems that result perhaps in customer quality problems, may have human resources problems, safety issues, scrap and yield issues, and so forth. Use SPC to understand that based on the data that is available. It's a set of practical problem-solving tools that assist our decision-making process in management and operations and quality. We're making decisions all the time. And you want to have a way to know when to do something and when not to do something, and how to, in which direction do you work. And that's what statistical process control can help you do. What's the advantage? It's making more money, bringing more cash into the bottom line, and growing the business, increasing quality, increasing productivity, making your business better, higher reliability, and a better name for your business. So you can use it for selection of suppliers who can provide a consistent raw material. Your purchasing department can work on that. Consistent and repeatable process changes so that your engineers know and your process people know when you've gone from one product or process to another that the quality is still there. Consistent gauging and measurement. All gauges are not the same, and that might be correlated to cost or might be related to simple setup or training. Your manufacturing people will want consistent output production, predictable, so they know how many parts they're going to get in what quality and quantity every day, smooth and dependable material flow, and so forth. In my experience, in terms of automation, it's impossible to use automation well if the raw materials, the components, and the parts coming to the automation have poor quality and they're random. I mean, a robot is really just a really complex, stupid device. It can't discriminate and on poor quality. It has to have poor quality, repeatable parts presented to it exactly in the same way every time. Use of statistical tools improve profit, cash flow, and growth. Again, I was introduced to SPC by the Ford Motor Company, and that was what they were interested in. As a business, they wanted to have high quality, they wanted to have happy customers, and they wanted to grow their business. And they did, and it worked. SPC allows us to know what can go wrong, what is going wrong, perhaps when it will go wrong, and what to do when it happens. And again, this is the quandary that most people in operations have, is what to do and when to do it. Problem solvers use statistical tools to identify and eliminate excessive variation and target the process. SPC, however, does not solve the problems. It's not a magic bullet. It points a solution, and you, as statistical problem-solving advocates, you must do the work to improve the process. So, a little review. What is quality? We talked about different definitions: fitness for use, conformance to specifications, and we talked about the losses associated with being off target and having too much variability. And your best quality is those parts and processes that are running right at target with minimized variation. And then we talked about what SPC is. It's a method to control a process by examining the available process or product information. It's a money-saving, problem-solving tool, and it's a management technique that operations and quality can use to know when to do things and when not to do things, and how to influence a process. It's a universally applied method that provides an opportunity to describe minimized variation on target and resulting in best quality at the lowest cost. And this is not a new technique, folks. This technique has been around since the 1930s and been successfully used in thousands and thousands of industries throughout the world. In our discussion of statistical process control, we'll be talking about this concept of variation to a great degree. I want you to get comfortable with that. So this slide speaks about observation, examples, and the principle. Observation of variation. Everything varies. Individual things and occurrences, however, are not predictable, but groups of things or occurrences form a constant system of causes which does tend to be predictable. For example, people live to different ages, right? And no one knows how long they will live, yet insurance companies can tell with great accuracy what percentage of each group will live to be certain ages, depending on where they live, their lifestyle, and so forth. Another example, you can't write the letter A twice exactly the same way, and you have no way of knowing how your next A will differ from the last one you've written. However, there is something unique about your A's that make them recognizably different than anybody else's. The principle is, again, that all patterns fluctuate. Individual things vary. Individual points are unpredictable, but the good thing is that a group of series of points from a constant process stream will tend to follow a pattern that obeys a fixed law. And we're going to learn what that law is and how to control and identify that variation. So our definition of variation is the inevitable differences among individuals within a particular group or class. And as we talked about, everything in nature and life exhibits variation. For example, if you go to the same grocery store, how much will you spend at the grocery store each week? How long will it take you to drive to work each day? The annual snowfall or rainfall in your county, the weekly demand for milk or whatever at your grocery store, how many Camaros GM are going to make this month, how many times 911 will be called in your city or any place. Individual product characteristics are normally different from each other. So the question is, if everything varies, what's normal variation? And we classify variation in two areas. One, common cause variation, and special cause variation. Well, we're going to show you some tools to be able to identify each and how to control it. So just to further advance our discussion about variation in all things in nature and in manufacturing, and as we spoke about just a few minutes ago in the PowerPoint, the definition of variation is the inevitable differences among individuals within a particular group or class. So I raided Walmart the other day and I selected some samples that might be indicative of this type of variation example. You'll see these on the store's shelves. It's nothing unusual. I have a scale here, a little weight scale, and I'm going to turn it on and calibrate it with this little bar just to make sure that it comes back to the same number over and again. So we'll start with the bottled water. 18.2 ounces. $18.2 ounces. $18.1 ounces. $18.24 ounces. $18.24 ounces. $18.2 ounces. So there's nothing wrong with these products. This little example just illustrates that there is variation in the products that you see in the market, and that variation is normal. How about little packages of dry soup? Now, in here is the carton itself, variation in the cardboard, might be variation in the little packages in there, and also there's some variation in the noodles as well. 6.14 ounces. 6.10 ounces. 6.10 ounces. 5.96 ounces. 5.43 ounces. So you might think this might have a bit more variation because of the multiple components that are in the package. Good. How about tomato sauce? 17.11 ounces. 16.93 ounces. 17 ounces. 16.79 ounces. 17.32 ounces. 17.14 ounces. Good. Cans of albacore tuna. 5.71 ounces. 6.17 ounces. 6.07 ounces. 6.28 ounces. 6.38 ounces. 6.28 ounces. So the tuna fish has got a bit more variation that you might expect, but because it's a natural product and it comes in chunks. It's going to be a bit different in terms of its variation than water, which is a fluid. How about these protein bars? .80 ounces. 1.98 ounces. 1.83 ounces. 2.05 ounces. 1.90 ounces. And 2.12 ounces. So the protein bars, again, are a little bit chunky product. It's a baked product, so there's going to be a bit more variation than you might again see in fluids such as, fluids such as water or the tomato sauce. Examples of natural variation. Again, the definition of variation is the inevitable differences among individuals within a particular group or class. So this is table just is a summary of all those numbers that I was recording on the sheet just for your information. I've also included the average and range. The range is the difference between the largest value and the smallest value within each subgroup for your review. So we've defined variation as the inevitable differences among individuals within a particular group or class. Variation's normal, and we see that in everything in life, everything in nature, everything in manufacturing. Every product has variation. Every process has variation, and it leads to variation in the product. And what we'd like to do, we'd like to control that variation and understand if that variation produces products that's different than normal. You may recall that we illustrated that products have variation by weighing some products from the grocery store. We weighed some cans of tomato sauce, some boxes of dry mix soup, some power bars, some cans of tuna, and some bottles of water. And they had variation, and that's normal. Variation in weight. Again, we'd like to understand if everything varies, we'd like to know what is normal variation and be able to differentiate the difference between common cause or random variation or normal variation from what we call special cause or abnormal variation. And perhaps we can illustrate that by using this tool that you see in front of you. It's called a quincunx. This quincunx is produced by the Lightning Calculator Company from Troy, Michigan. And so what we have here is a nest of, or accumulation of balls. Think of this as a process, and they're going to be processed down the chute, and they're going to go into this nest of pins, and the balls are going to have the opportunity to drop one way or another as it strikes each pin, and they're going to be accumulating down here. We've drawn some specification limits, some lower specification limits and upper specification limits to illustrate the process. Hopefully we're making good parts. As we can see, each ball falls through the little pin arrangement, and it's impossible to predict where each ball will fall through there. But isn't it interesting that this process does produce this distribution which is predictable? in that are two process parameters that we're interested in, and that is the center of the distribution and the width of the distribution are easily visible. So the center of the distribution is about here, and the width of the distribution is about here. So we say that process is running in pretty good control. But what happens if something happens? Some process parameter changes. Maybe different materials introduced in the process from a different supplier, or their supplier's process has somehow gone uncontrolled and it's introduced into your process and you don't know that it's changed. Or perhaps a setup parameter has been changed in one of your machines and now the process is different and it's producing products differently. Now you can't inspect every product, every part all the time. So how in the world are you going to be able to detect this process shift? Well, we're going to illustrate that by that process shift by changing the position of our chute here. And you might expect, let's just say that we're making the same product, yet somehow, unbeknownst to us, raw materials or machine controls or something else has crept into the process, and now a small fraction are out of specification. And we, since we're not measuring every part, don't know about it. And those parts that are out of specification are going to our customer. So these parts now are beyond the specification limit. So in the next section, we're going to be describing the use of statistical process control charts, and they're going to be very useful in illustrating how we can detect changes in the process, that is, changes that create special cause variation that produce parts that are beyond the specification limits. So you saw in the example of the use of the quincunx, the little beads falling through that nest of pins created a normal distribution, or what approximated a normal distribution. But before we get beyond this point, I just want to have, again, a few definitions that we can work with. Frequency distribution and histogram. Frequency distribution is a graphic presentation of the set of all various values that individual observations may have and the frequency of their occurrence in the sample or population. You also can have a frequency distribution of averages. A histogram is a plot of the frequency distribution in the form of rectangles, and the bases of those rectangles are equal to the cell interval, and the area of the rectangles is proportional to the frequency. And you can see pictures of a frequency and histogram right below the definitions. So let's take a look at some frequency distributions and histograms and try to learn something about them. In this case, you see a frequency distribution and histogram, a familiar bell-shaped curve. And very quickly, because it's a graph, you can see that the average is about 74 and the range is about 6. Well, the range is the difference between the largest value, in this case 77, and the lowest value, which is 71 in terms of the cells. But not all distributions are normally distributed. For example, here's a distribution of golf league scores. For example, if this happens to be an after-work league, you're going to get 36 holes in, perhaps, at the end of the day. The target there, you can see, is about 36. You see very clearly that most of the players on this league are not that good. Some there on the left are pretty close to target. So you might want to say this distribution has two modes, sometimes characterized as a bimodal distribution. How about bowling? bowling scores. Well, maybe the same athletically inclined people are on the golf league are also on the bowling league. See, the better players, the ones off to the right, have more higher scores since the objective is to get closer to 300, and on the left, the folks who are having a lot of fun and not scoring so well. A truncated distribution can be characterized as one like this, plant seniority. You have a lot of employees that are usually new with a company and very, very few employees that have a very high seniority, sometimes known as a skewed distribution or a truncated distribution. So to give you a little practice in creating your own frequency distribution, here's some data. And if you just take a look at the data doesn't tell you very much at a quick glance, but what I invite you to do is use this opportunity to plot your own frequency distribution. There's a form at the end of part 2 that you can use at this point to plot your own frequency distribution from the data. This is what it looks like from the data. Again, the distribution is typically like a bell-shaped curve with the average about 74 and the range of about 6. So frequency distributions are there to tell you about the data. They don't tell you about any time parameter. It doesn't tell you whether the 74s occurred at the beginning of the shift and the 72s or 78s at the end of the shift. It just tells you about the data as collected. Well, if we were to enter a population of individuals and collect those individuals, and I've got 100 samples collected from a known distribution here, and then on the right, if you take the first 5 and add them up and divide by 5, create an average, and write that average off on the right. Take the next 5 and calculate that average. You have 2 different distributions then. You have a distribution of individuals, and then you have a distribution of averages. And it's going to be very important for us to know how to use both these techniques of understanding the difference between individuals and the distribution of averages. So if we were to plot those 100 individuals and create a frequency distribution histogram, you'd see that the center of the distribution was about 30, 31, and the width of the distribution was roughly 60, the difference between what you see about 60 and about 3.6. However, the distribution of averages is significantly different. Well, it's the same from one perspective in that the center of the distribution of individuals and the center of the distribution of averages is exactly the same, while the width of the distribution of individuals is wider than the distribution of averages, and that's really a function of sample size. But the point here is that they are different, and the distribution of averages is narrower. So if you were to consider a normal distribution and you split it up into, in this case, 6 equal widths, there's something that, and you call each one of those widths a standard deviation. Standard deviation, think of it just as another way to speak about width. Just like we spoke about range before, standard deviation is another way to think about width. The bigger the standard deviation, the wider the distribution, smaller the standard deviation, the narrower the distribution. Well, the interesting thing that we know about the normal distribution is that when you find the center and you go out 1 standard deviation from the center, you find that that's 68% of all the individuals, 68% of all the objects. And if it's a distribution of averages, 68% of all the averages are within 1%, plus or minus 1 standard deviation of the center, plus or minus 2 standard deviation from the center. From the average, 95% of all those things, and 99.73% of all of the items, the individuals, and if it's a distribution of averages, all the averages fall within 99.73% of the center. So key to understanding the use of statistical process control charts is something called the central limit theorem. And that is sample averages form normal distributions. When you take a look at an SPC chart, think of the distributions that you've been seeing sort of on a horizontal plane, standing up on its edge, and think of them in the vertical. And the upper and lower control limits represent or will represent plus or minus 3 standard deviations of the averages. So central limit theorem says when you select from averages from a distribution of individuals, those averages form the normal distribution. Let's have an example. When you think of a deck of cards, a deck of cards is certainly a non-normal distribution. If you assign numbers to every card, for example, 1 to an ace and 13 to a king, if you were to plot that distribution of individuals, you could form something called a flat distribution. That slide will be coming up. So what would you think the distribution of averages would look like in a deck of cards? So the distribution of a deck of cards, using 1 as an ace and king and 13, you can see that you can plot it yourself. In that there is going to be 4 of each. 4 aces, 4 twos, 4 threes, 4 fours, all the way to 4 kings, which is designated by 13. So you look at this distribution, it's clearly not bell-shaped, sometimes known as a uniform or a flat distribution. This is a distribution of individuals of a deck of cards. What do you suppose the distribution of averages look like? What you see now is a sampling, repetitive sampling of a deck of cards. So you have 25 samples or subgroups and 10 samples within each subgroup. And again, 11, 10 would mean that was a 10, 11 would have been it's a jack, 6 would have been a 6. And then if you add each sample subgroup up and divide by 10, you'll find on the right-hand side a listing of the sample average. Individuals on the left, averages on the right. So what do you suppose that distribution of averages looks like? Well, from that listing of data on the previous page, you can see that the distribution of averages of a deck of cards is clearly not uniform. It forms, just like the central limit theorem said it would, it forms a normal distribution. So when we talk about distributions and populations in the future, and the key to using statistical process control limits that are calculated based on the normal distribution, you can think back to this example of a deck of cards was clearly non-normal as individuals, but it forms a normal distribution, just like the central limit theorem said it would. Well, I want to thank you for your attention in the first part of our statistical process control clinic, and hope that you continue to part 2, where we're going to have lots of fun illustrating unknown process and showing you how to calculate statistical process control limits, identification of out of control conditions, that is the difference between special causes and common causes. And then at the end, we're going to be talking about attribute control charts, how to control variation, how to identify variation in attributes. Thank you very much.